Imagine sitting under a tree on a warm summer day. A gentle breeze rustles the leaves. Suddenly, an apple falls from the tree, landing with a soft thud on the ground beside you. Most of us would simply pick up the apple or let it be. But for one young man, this simple event sparked a profound question that would change our understanding of the universe. That young man was Isaac Newton, and the falling apple would become a symbol of his groundbreaking discovery, the law of gravity. The story of Newton and the apple has been told and retold for centuries. It's a tale that captures the imagination, reminding us that even the most commonplace occurrences can hold the seeds of scientific revolution. The apple, a symbol of knowledge and discovery, became intertwined with Newton's legacy. But the true story, as with many historical anecdotes, is a bit more nuanced than the legend. Isaac Newton was born in 1643 in Woolsthorpe, England, a small village nestled in the English countryside. This quaint and serene environment would be the backdrop of his early years. His childhood was marked by both solitude and a thirst for knowledge. From a young age, Newton displayed an insatiable curiosity, often found with his nose buried in books, seeking to understand the world around him. He was a quiet and introspective child, preferring the company of books to that of other children. This preference for solitude allowed him to delve deeply into his studies, fostering a profound sense of wonder and inquiry. This inclination towards solitary study would stay with him throughout his life, shaping him into one of history's most independent and revolutionary thinkers. Newton's ability to focus intensely on his work, undistracted by social interactions, was a key factor in his groundbreaking discoveries. Newton's early education was not particularly remarkable. He attended the King's School in Grantham, where he showed an aptitude for mathematics, but was otherwise an unremarkable student. His teachers noted his potential, but it was his self-driven exploration that truly set him apart. At the King's School, Newton's interest in mathematics began to blossom. He was fascinated by the logical structure and precision of mathematical concepts, which provided a foundation for his later work in physics and astronomy. However, his inquisitive nature led him to explore the world around him, conducting experiments and building mechanical devices. He was particularly interested in understanding how things worked, often taking apart and reassembling objects to learn their secrets. This hands-on approach to learning would later become a hallmark of his scientific method. Newton believed that true understanding came from direct observation and experimentation, a principle that would guide his work throughout his life. At the age of 19, Newton entered Trinity College, Cambridge. This was a turning point in his life, as the university environment provided him with access to a wealth of knowledge and intellectual stimulation. It was here that his intellectual horizons expanded dramatically. Surrounded by some of the brightest minds of his time, Newton was able to engage in deep discussions and debates, further fueling his passion for discovery. He immersed himself in the works of Galileo, Kepler, and Descartes, absorbing their ideas about motion, astronomy, and the nature of the universe. These texts provided a rich source of inspiration and a foundation upon which he would build his own theories. Cambridge provided fertile ground for Newton's genius to flourish, surrounding him with like-minded scholars and exposing him to the latest scientific advancements of the time. The collaborative and intellectually stimulating environment of the university was crucial in shaping Newton's future contributions to science. The story of Newton and the falling apple, while a captivating anecdote, is likely an embellishment of a real event. This tale has been passed down through generations, often with the dramatic detail of an apple striking Newton on the head, leading to his groundbreaking discovery of gravity. There is no evidence that an apple actually struck Newton on the head. The story, as charming as it is, seems to have been exaggerated over time to create a more compelling narrative. However, historical accounts, including those from Newton himself later in life, suggest that he did observe an apple falling from a tree in his garden. This observation was a pivotal moment that sparked his curiosity about the forces at play. This observation, rather than a bonk on the head, triggered his thoughts about the nature of falling objects. Newton began to ponder why objects always fell straight down, rather than sideways or upwards. Newton, already deeply interested in the laws of motion, was likely pondering why objects always fell straight down. His mind was already attuned to the mysteries of the natural world, and the falling apple provided a tangible example of a phenomenon he had been contemplating. The apple, a tangible example of this phenomenon, provided a focal point for his thoughts. It was a simple, everyday occurrence that held within it the seeds of a profound scientific revelation. It's important to note that Newton's genius didn't lie in simply observing the apple fall, but in asking the deeper question, what force was pulling the apple towards the earth? This question was the beginning of a journey that would lead to one of the most important scientific discoveries in history. This seemingly simple question held the key to unlocking a fundamental force of nature. Newton's curiosity and his ability to ask the right questions were crucial in his scientific endeavors. Newton's contemplation of the falling apple was not a sudden epiphany, but rather a catalyst that set in motion years of meticulous observation, experimentation, and mathematical analysis. His work was characterized by a relentless pursuit of understanding and a methodical approach to uncovering the laws of nature. It was through this rigorous process that he would eventually formulate his law of universal gravitation. This law, which describes the gravitational attraction between masses, revolutionized our understanding of the universe and laid the groundwork for modern physics. Newton's insights extended far beyond the simple observation of a falling apple. His work on gravitation was part of a larger framework of scientific principles that have shaped our understanding of the natural world. His contributions to mathematics, optics, and astronomy are a testament to his unparalleled intellect and curiosity. Today, Newton's laws continue to be fundamental in various fields of science and engineering. From space exploration to everyday technology, the principles he discovered centuries ago remain as relevant and impactful as ever. So, while the story of the falling apple may be more fiction than fact, it symbolizes the spark of curiosity and the quest for knowledge that drives scientific discovery. Newton's legacy is a reminder that sometimes the simplest observations can lead to the most profound insights. Section 4. Gravity's pull, a revolutionary idea. Newton's great insight was that the same force that pulls an apple to the ground also governs the motion of the moon around the Earth and the planets around the sun. This realization was groundbreaking, as it connected the seemingly mundane with the celestial. He called this force gravity, from the Latin word gravitas, meaning weight. The term itself carried a sense of importance and seriousness, reflecting the profound nature of his discovery. This was a revolutionary concept, uniting the heavens and the earth under a single universal law. It suggested that the same principles that govern the fall of an apple also dictate the motion of the stars and planets. Prior to Newton, the prevailing view was that different laws governed the celestial and terrestrial realms. Scholars and scientists believed that the heavens were governed by divine or mystical forces, separate from the physical laws observed on Earth. The motion of the planets was seen as a matter of divine order, distinct from the earthly phenomena of falling objects. This dichotomy created a divide in understanding the universe, with celestial events shrouded in mystery and earthly events explained through observable phenomena. Newton's law of universal gravitation shattered this dichotomy, proposing that the universe operated on a set of consistent and predictable principles. His work suggested that the same mathematical laws could be applied to both the heavens and the earth, providing a unified framework for understanding the cosmos. Newton's law of universal gravitation states that every object in the universe attracts every other object. This attraction is not limited to large celestial bodies, but applies to all objects no matter their size, with a force that is proportional to the product of their masses. This means that the more massive an object, the stronger its gravitational pull, and inversely proportional to the square of the distance between their centers. This inverse square law indicates that as the distance between two objects increases, the gravitational force between them decreases rapidly. This elegant equation provided a mathematical framework for understanding the motion of everything from falling apples to orbiting planets. It allowed scientists to predict the behavior of objects in space and on Earth with remarkable accuracy, revolutionizing our understanding of the universe. Newton's work was published in his seminal book, Principia, which laid the foundation for classical mechanics. This work not only changed the course of science, but also influenced the way we perceive the world around us. Today, Newton's laws continue to be a cornerstone of physics, guiding modern scientists in their quest to understand the universe. His revolutionary idea of universal gravitation remains one of the most profound discoveries in the history of science. Section 5. Unraveling the cosmos, gravity's impact. The impact of Newton's discovery of gravity on our understanding of the universe was profound. It provided a unifying principle that explained a wide range of phenomena, from the tides to the orbits of comets. It also allowed astronomers to make accurate predictions about the motion of celestial bodies, transforming astronomy from a largely observational science into a predictive one. Newton's law of gravity became a cornerstone of classical physics, influencing generations of scientists and shaping our view of the cosmos for centuries. It laid the foundation for our understanding of celestial mechanics, allowing us to calculate the masses of stars and planets, predict the existence of Neptune based on irregularities in Uranus's orbit, and even launch spacecraft with pinpoint accuracy. Beyond its scientific impact, Newton's discovery of gravity had a profound philosophical impact. It replaced the Aristotelian view of a universe governed by mystical forces with a clockwork universe, operating according to predictable laws. This shift in perspective paved the way for the Enlightenment, a period of unprecedented scientific and intellectual progress. Section 6. Beyond gravity, Newton's other discoveries. While Newton is best known for his law of universal gravitation, his contributions to science extended far beyond this groundbreaking discovery. He was a true polymath, making significant contributions to mathematics, optics, and even alchemy. His work in these diverse fields demonstrated his remarkable intellect and his insatiable curiosity about the world around him. One of Newton's most important contributions to mathematics was his development of calculus. Calculus is a branch of mathematics that deals with rates of change and accumulation, providing powerful tools for analyzing motion, curves, and other continuous phenomena. Newton developed calculus independently of Gottfried Wilhelm Leibniz, who is also credited with its discovery. Calculus revolutionized mathematics and physics, providing a new language for describing the natural world. It became an essential tool for scientists and engineers, used to model everything from the flow of fluids to the behavior of electrical circuits. Newton's development of calculus was a testament to his mathematical genius and his ability to create entirely new branches of mathematics to solve the problems he encountered.